So today we're going to start talking about schematics. So we're going to go through the basic schematic symbols, and we're going to talk about how we're going to actually design our schematics on the computer, and then we're going to actually start our tutorial on some of the Cadence design tools we'll be using, namely the Allegro Design Entry CIS. So we'll be doing that live here. So if you've already installed it on your laptops, you can follow along, and if not, you can watch this and try and remember, and I'm going to try and record all of this to put online later as well. So with that, let's first talk about what we're going to be using to design our schematics. We're going to be using products from Cadence. Cadence is one of the largest CAD tools vendors on the planet, so we're using their tool chain. We have between 300 and 600 seats for each Cadence product that Stanford is licensed for on our license server, so there's plenty of space for everyone to use the PCB design tools. I've never seen more than about 3 people on it, 2 of whom are myself and someone else in our group. So we have plenty of licenses for what we're doing. We're going to be using Allegro, and it's also listed as SPB 15.7, so this is the current release from Cadence. This is an industry standard program. This is not something you're just going to use here at Stanford. I think Apple Computer uses Allegro. There are all sorts of companies that use Allegro. Allegro and OrCAD are basically the same program. I think Cadence bought out OrCAD a while back. So they're pretty much interchangeable. The user interfaces are identical. And in fact, the schematic capture software is the same, just has a slightly different feature set. So we're going to be using Design Entry CIS for our schematic capture. So that's the name of the program you're going to launch. There's a whole lot of programs that will install, including Design Entry HDL, which we're not using. So make sure you run Design Entry CIS. This exact same program for schematic capture, I mean, from what I can tell, it's even the same executable file, is also called PCB Design Studio or PCB Design Expert as part of the Allegro tool set. If you use the XL option, which I recommended you guys do in your install notes, that becomes PCB Design Expert. If you use just L, it becomes PCB Design Studio. And there's a minor feature set difference. For this class, it doesn't really matter either way. XL will give you some differential routing help and some things like that. The same program also is called Capture CIS or OrCAD Capture. So once you learn how to use the software here in this class, you can use all of these programs because they're all the same. So that's what we're using for schematic capture, and that's what we're going to start with today. So that's how to take a schematic design that you're thinking of in your head and put it into a computer. Later on, probably next week, we're going to talk about Layout Plus, and Layout Plus is the tool we're using for actual printed circuit board design, for actually designing the copper traces on a circuit board. And we'll talk in depth about what you need to have on that PC board itself and then how to actually do the CAD. Now you may notice when you're installing some of these tools that it has an option for network parts libraries. And that's basically where if you're in a corporation, you can have a centralized location for all of your schematic symbols, which you guys will really wish we had when you start working on this. But for this class, we're not using it. So for this class, you guys have to make your own schematic symbols that don't come standard with the tool set. And this is the most important part about this program, especially here at Stanford. The most important part is please be patient when you're starting the software. I don't know why this is. No one here seems to know why it is, and Cadence hasn't been able to help us. But sometimes it'll take you upwards of 15 minutes to check out a license. So that means when you click on Design Entry CIS, nothing happens on your screen, not even a window popping up, for like 15 minutes. If you just keep opening more and more and more copies, it's going to just flood your computer with processes, and then all of them are going to open at the same time, or none of them will. So, yeah.
Is this only on install? Or?
So the question is this only on install? And unfortunately, no. It's every time you launch the program. Sometimes it's really fast. Yesterday I was in the cluster checking it out, and it would register in 5 or 10 seconds. Then yesterday night in my office, it took 20 minutes or so. So you never know. So the big rule is, start up the program. If it doesn't show up immediately, don't try and run it again. It may not show you anything on your screen. If you really want to check and see if it's running, you can go to Task Manager and look for capture.exe and see if it's running. It probably is. It won't be doing anything. Go get a cup of coffee, take a breather. Don't just keep running the program. Again, I don't know any solutions for this. Valentine, our CAD administrator here, does not know anything about how to fix this. No one seems to know. But there are a few pointers that I would like to give out as well in the realm of licensing. So licensing comes from 3 different servers located in CIS, which is different from Capture CIS. It's the CIS building by Packard. There's a website that's on the slides that you can go to. It will give you information about all of the CAD tools we have. This includes for VLSI design, for making ASICs, things from Mentor Graphics, things from everybody. Look for Cadence. Remember that the Allegro tool set that we're using is by Cadence. And you can check the license manager status towards the bottom. It has a little link and it says Cadence, and it'll say like status users or everything. So you can click on that and make sure the license servers are actually up and running. There's also a CAD tools mailing list. And if you run into big-time licensing problems and you can't get anything working, or if that status page shows that one of the license servers is dead, email the CAD tools mailing list. So unfortunately, I'm just a user of the CAD tools just like you guys. I don't run the license servers. So if they hose, you have to talk to the guys that actually maintain the license servers. So any questions on this tool chain and about being patient starting the program? If you keep starting it over and over and over, it won't work, I promise. All right, so next up, I just want to go over a couple basic schematic symbols and designators. And this is important because you're going to be using them all the time when you make schematics. So if I were you, I would try and memorize them, like before next class. Hint, hint. They're not very hard, but they are important. So if you look at the very upper left, the very first symbol is a resistor. A resistor is the squiggly line. It's designated by R. So the designator is the single letter abbreviation that you use when you have these on schematics. So you can see there that's called R1. It's because it's the first resistor on the schematic. Now you notice that all of these components have little square blocks, or at least a lot of them do, at the end of the net. And that just indicates a place where you can tie off a net or a wire. And some of them don't, like this voltage regulator designated U2 in the center. Don't worry about that. But if you see one of these little square blocks, it just means that that's a point you can tie off to. You also can tie off to the pins in the voltage regulator. It just doesn't have the square blocks. So those don't have any particular special meaning. So below the resistor, there are 2 different types of capacitors. C1 is a non-polarized capacitor. So that's typically a ceramic or a thin film capacitor. That means you can put it in either direction. It doesn't have a positive or negative side. The one below that is a polarized capacitor, C2. So a polarized capacitor is typically like tantalum or electrolytic. Polarized capacitor is polarized, which means if you put it in backwards, it'll explode. It won't work. So polarized capacitors you typically can find in much higher capacitances. So for example, on our boards, you'll be using probably some 10 or 20 or even 100 microfarad capacitors there. Those are going to be polarized. Those are going to be tantalum. The non-polarized capacitors are much smaller. They're going to be like 1 microfarad, 0.1 microfarad, 0.01, something on that order. And those you can think of as being like much faster at supplying current than these tantalums. They have a much lower equivalent series resistance, so they're faster for kind of like high speed. So I'll show you later on today, when you have pins that you need to bypass with capacitors, you're trying to supply power to it, you'll need to put a polarized capacitor and a non-polarized one right next to each other. That's the best way to go about it. So non-polarized cap, doesn't matter which way it goes, small values. Polarized cap, it matters which way you put it in, and it's typically for higher values. The last symbol on the left-hand column is an inductor. So you'll use that to bypass, for example, the power supply on going into your analog to digital converter for noise. And you're depending upon what DAC we end up using and what headphone driver, you may need some inductors there as well. So the second column, very top, is a crystal. So that's the symbol for a crystal. This is like the quartz crystal that you would use for your oscillator. So remember, we talked about these, I believe it was last class. So on your board, this is the ABM8 type crystal. This package only has 2 wires. The ABM8 has 4, so it's going to be a slightly different symbol. But the symbol itself is for a crystal, and its designator is always Y. And then below that, we have 2 different diodes. We have an LED, which has the arrows coming out, indicating little photons coming out. And the very bottom diode is just a regular diode for reverse bias protection or clamping or whatever it is you're doing with it. So diodes, whether they're LEDs or regular diodes, are designated as D. So this is all very straightforward, hopefully. The funny resistor, designated R2, is a potentiometer. It's one that you can turn. It's a variable resistor. So you'll notice that there's a constant resistance between the left and the rightmost nodes, and there's a center node that's the wiper, and that goes across to make a variable resistance. So again, these are all pretty common symbols. So potentiometers have the same designators as regular resistors. They're both R. So when you're looking at your bill of materials, it's important to realize that just because it says R doesn't mean it's a fixed resistor. You may have put in a potentiometer somewhere, and that means you need to order a different part. So just keep this in mind. So below that, I have this AN77L something part. This is an integrated circuit. And so all integrated circuits, all the chips that you have a designator of U. Now, transistors by themselves have different designators, but just like an IC actually has a designator of U. So this is one part, for example, that's a voltage regulator. It's got 3 terminals, an output, an input, and a ground. So it takes in some arbitrary voltage, and it converts it to some other arbitrary voltage depending upon the part number constantly. Then below that we have the push button switch. So hopefully you can find most of these types of schematic symbols on the schematic for your development board. I recommend looking at that schematic a lot because that's a really good reference to start from. So in the upper right there are 2 small symbols, and they're kind of obscured by the block indicating where the node is, but there's the VCC symbol, which is just a power symbol, and it doesn't have to be VCC. You can name it whatever you want and it will be a different rail. And then you have ground, and ground is ground, and you don't rename ground. All of your grounds are the same. But for example, you can have a 3-volt rail and a 5-volt rail that both use that VCC symbol, but they're still different. So if you look at the schematic for your development board, there's a 3V0 or 3V3, indicating a 3.0 or 3.3 volt rail. And there's another one that's labeled 5V0. That's the 5-volt rail. But they both have the little arrow shape. So you use those to indicate what lines are power rails versus just signals going around. And then lastly down here I have a 9-pin connector. It's just some arbitrary 9-pin connector, and its designator is J. And J you will also use for jumpers if you just have 2 pins or 3 pins sticking up to select an option. And one other thing I'd like to point out is that on here you have the designator, for example R1, and then below it, right now it says resistor. When you start creating your schematic, you will replace the word resistor with whatever the actual value is. So for example, if you want a 180 ohm resistor, you'd replace the word resistor with 180. Or on the capacitor, C1, instead of saying cap NP, you would say 0.1 UF for 0.1 microfarads. So these are just there. This is what it will default to when you use capture. It'll show you the name of the part so you kind of know what it is. But then before you actually finish your schematic, you need to replace those names with the actual part. Yeah?
When you replace crystal with the frequency oscillator or the part number?
All right, so the question is, what would you do with crystal? Typically, you'd put the frequency, although sometimes you'll put a specific part number if that's what you really care about. For example, on LEDs, you may indicate the color, or you may give a specific part number. It's kind of up to you. Generally, you'll keep it a bit more generic, and then have the part number explicitly called out later on. However, with integrated circuits, you usually put the part number, because that is what the chip is. Yeah?
In some simulators, the crystal, like in order to be able to change the value of the crystal, you change like the components, well, like resistor, capacitor, and inductor, because the crystal can modify those three components. Is it the same, or you can just like change whatever you want?
Okay, so the question has to do with if you're using a simulator, do you need to model a crystal with other parts that are linear? And you do not. So this is just schematic capture. This is what you actually want to create on the board. And on the board you're designing, you want to actually put a crystal in. So this isn't a simulator. This is just for the actual schematic. So if you want to have an RLC oscillator or something like that, then you can put that in, but that's what you're actually going to translate to the board. But parts in general will translate from one schematic symbol to one part. And there are some exceptions where you may have, for example, 4 op amps in a package. And you'll have 4 different symbols in your schematic, but they are boiled down to one actual chip. But in general, it's roughly a 1-to-1 translation between what you see here and what goes on your board. Yeah?
If you want multiple grounds, do you have to use a different ground symbol?
All right, so the question is if you have multiple grounds to use the different ground symbols. So sometimes you will have more than one ground. So for example, you have an earth ground and a logic ground or an analog ground, and you will need to use different symbols for that. because that also makes it clear to the reader which is which. And there are multiple ground symbols available that indicate these different types of grounds. So any other questions on designators, schematic symbols? So these are the symbols we're using in this class. You may find different symbols in other places, but these are pretty standard. So again, I recommend you remember what the designators are for the different symbols for the different parts. Yeah?
So when do we want to separate analog ground from digital ground?
All right, so the question is, when should you separate analog and digital grounds? And that's a complicated topic. So if you're using an analog to digital converter and you're doing something that is high performance, typically you'll need to look at the data sheet for the analog to digital converter, and it will tell you explicitly where the split is between analog and digital. And you'll have separate ground planes that split sometimes underneath the chip or sometimes just off the chip. But those types of designs are tricky. They're more than a 1 semester or 1 quarter class. Yeah?
Is that because of noise? The digital line's noisier, you don't want that?
All right, so the question is, why do you separate your grounds? And it is for noise. So a digital line running over a ground plane is going to put some noise on that ground plane. And your analog signals probably will as well, but you want to keep that noise as low as you can for analog signals. So any other questions on these? All right, check with you on Thursday. So let's go through some basic nomenclature of the schematics itself. And this nomenclature is fairly generic, but it's also specific to Allegro. In other words, this is the nomenclature that Allegro will use, and in the real world, sometimes you'll use some other terminology or slang. So a part is an actual component on your schematic. And again, you may have 4 different parts that go down to 1 chip, but it's still, a part. So then there's something called nets, and we've kind of glossed over this in previous lectures when we're looking at the schematics, but nets are what you actually connect parts together with at their pins or nodes. Okay? So nets are sometimes called wires, but that's a little weird to think about, because a net on your schematic just indicates where connectivity should be. It doesn't indicate what order things get connected in the real world. It just shows what nodes are connected to each other, or what pins are connected together. Does that make sense? So then you can name nets with something called a net alias. And so if you have a signal that's like, for example, ground, you can just label a net ground and it'll magically connect to anything else that's called a ground. So if you have just a little short stub of a net somewhere and you put an alias on it, that little short stub is electrically going to be connected to any other net that has the same alias. That's very important to remember, because you may look at some schematics and the schematic will have parts all over the place and no wires actually connecting things together. And all it will do is have net aliases right next to all the pins. So those are kind of hard to read because you have to figure out where these net aliases go, but it still is technically correct. So remember that if you name 2 different things, for example, button 1, they're going to get connected together. So you can inadvertently short nets together by doing this. So be careful. Well, now if you have a whole lot of nets, for example, if you have an address bus where you have maybe 16 bits worth of address or 16 bits worth of data, you can put all of those 16 nets into one trace that goes across your schematic called a bus. And in this case, for example, you can call the bus mem and then open brace 0.15 close brace. And that'll have nets internally that's mem0, mem1, mem2, mem3, and so on up to mem15. So that's 16 different nets that are contained within a single line on the schematic. I'll be showing you guys examples of all this here in just a few minutes. So a bus is what you can use if you have common address lines, common data lines, or just any general bus of signals that you want to have named sequentially. And this square bracket 0.15 is Allegro and OrCAD and Cadence's nomenclature for having multiple entities. Questions so far? Yeah. So the question is, are you going to drag and drop or type and click? And I was going to drag and drop, but if you'd rather type and click, you're welcome to do that. I'd recommend against
I
it.
thought you were mentioning how to type the and stuff.
No, this is the name of the bus. So when you put an alias on the bus alias will need to have a square brace and then a one number dot dot a second number. And that will have the range of those numbers in the bus, concatenated with whatever's before that, in this case min. Other questions? Okay. So there are things called off-page connectors, which you need to use if your net or bus goes off the current schematic page and onto a different schematic page. And again, there's a special button for this. I'll show it to you guys. But you have to make sure that in order to get connectivity between schematic pages, that the nets have one of these off-page connectors somewhere on the page. Yeah?
So the aliases don't connect across pages?
So the question is, the aliases don't connect across pages. And I think technically they don't, but I wouldn't trust it. So try to avoid namespace contention, so to speak. Try and keep your aliases unique, unless you want them connected. But to guarantee off-page connectivity, you need to use the off-page connector. This also makes readability a lot better, because there are ways you can back annotate and get the page numbers that have that particular net or that particular bus connected. So that's useful when you're trying to trace down where a connection goes. Okay, and as we also talked about on the last slide, there's a power and ground symbols. And really, you just put these to make it clear what nets are for power and ground versus what nets are just signals. But this will also give some hints to your layout program that, like, hey, these are power lines and not just signal lines. And that has an impact on the way that you route those nets. For example, with a signal, you can just kind of daisy chain everything together. You know, into one component, then out, and then into the next component, then out, and then into the third component, and out. And in power, you don't necessarily want to do that, because then the very last device on that daisy chain is going to potentially have a lower voltage. Most likely will have a lower voltage. So you can do different topologies like a star topology, or you can actually just have power planes. So putting these symbols on is a good visual aid for you to remember what is power, and it's a good hint to your layout program to help it know what is your power as well. So please do use them. And the last big part of the schematic nomenclature that I could think of is no connects. So no connects are used to indicate pins that are not connected to anything. It's just a little X. So remember all those gray square boxes that were on the components. If you don't want it to be connected to anything, put a no connect. Otherwise, when you're running some of your design rule checks or things like that, it may complain to you that you have a non-connected pin. It's also good when you just visually are going back over your schematic and you want to make sure, did I connect everything? Did I forget anything? If you have a no connect there, it means, yes, I've thought about it and this really isn't supposed to be connected. So please do use them. And that's going to be a requirement for designs you turn in this class. Don't just have floating pins. So any questions on basic schematic nomenclature here? All right, so I want to give you guys a few keyboard shortcuts. I'd recommend just printing this out and keeping it next to your computer. So these are the most common shortcuts you're going to use. You're going to end up memorizing them whether you like it or not, because you're going to do enough of this in the next 4 weeks that you'll remember. So you can use P to bring up the Add Part dialog. Now all of these different keyboard shortcuts also have buttons associated with it, or at least most of them do. And most of them also have a menu option associated with it. Now there are a couple that are kind of hidden. For example, C for center on mouse, I don't think you can find it on any button or any menu. It's kind of a hidden shortcut. But C will basically center your view wherever your mouse is. C is a good one to remember. So I, O, and C, zoom in, zoom out, and center, are what you're going to use to navigate around your schematic most. You can use the little sliders on the side and drag around, but when you start doing wiring and things like that, it's much, much faster to use these shortcut keys. And then on the left-hand side, we pretty much have all of the different entities that you can create up through and including place no connect. And then R will allow you to spin a part around if you don't like the way it's oriented. Also, on older versions of Allegro, your screen could randomly corrupt, where it just kind of didn't look quite right or things weren't connected. and F5 will redraw your screen. The newer version so far hasn't had that problem, but no guarantees. Redrawing is particularly important with layout, because in layout, things do get weird fast. So if you just notice something that doesn't look quite right, or if you thought you made a wire somewhere and it's not showing up, just hit F5 and make sure. So, again, I'd highly recommend you keep a cheat sheet like this nearby, at least for the first couple days. Another thing is I would really strongly recommend you guys start using this software this week. So I'm going to try and have your final design project, at least the criteria for it, handed out next week at some point, because it takes a little while to figure out how to use these tools. They're not complicated, it's just time consuming. So please do take a look at this earlier on, especially for licensing issues. If you have licensing problems at home, if you can't connect to the license server, again, the EE cluster has licenses, as well as the machines in our lab for office hours. So please do look at this software sooner rather than later and ask questions early. So any questions on what we've covered so far in this? Yeah?
What is the bus and the bus entry? How are they different?
All right, so the question is, what's the difference between a bus and a bus entry? So a bus is just this actual collection of nets together, which is like a line. And then when you want to draw a single net out of that bus, you put this thing called a bus entry, which is basically like a slash mark that goes from the bus to a net. So it's kind of a converter. Good question. Any other questions? Okay, so at this point, let's actually run Design Entry CIS. We're going to run our schematic capture software and just build some basic schematics and look at what it takes to create this.